Hello, so to continue our look at shorelines, glaciers and changing sea levels, chapter 14, we're now going to move on to glaciers and glaciation. And the first part of this is glaciation, past evidence, formation and movement of glaciers. And the first slide we have here is a look at evidence left behind by glaciers. And here we have a glacier, a mountain or a valley glacier in the photograph here, moving and carving its way down a valley, and as it does so, it removes and carves out a lot of material, as we see in this glaciated landscape in the middle figure here. One major aspect, or one major morphological change in the landscape are U-shaped valleys. So here we see a beautiful U-shape in this valley. You can trace this across in this way, and these are quite distinctive and are always really going to tell us that a glacier has once sat in that valley and has carved that particular shape in the landscape. And it's quite different to rivers. The rivers on land will always produce or always cut V shapes rather than U shapes. The next feature that we might come across here are these striations. These are linear scratches in bedrock, and these are formed when the ice moves across the bedrock, and any sharp clasts which are frozen into the base of the ice scratch these lines. Okay, so we might often see these, a number of these in parallel across the surface of a polished bedrock remnant. Glacial till is the collective term for all the material that the glacier has carved out, transported and redeposited. So we're really seeing till, which underlies the whole transport distance of the glacier, and we also see a lot of it at the end, the margins where the glacier sat, and a lot of these melt out channels, as we see here, brought further material down valley. We also have what are known as glacial erratics. These are boulders, and as we see here, we've got an example of a very large one. Some of these can be the size of houses, but these are known as erratics because they typically look in unfamiliar surroundings when they come to rest. And these are pieces of perhaps the valley walls here, which have been carved out by the ice as it comes down the valley, carried on top of the ice or slightly entrained in the ice, and then they're dumped off the side. So these are kind of rolled off the side of the ice here, and we've now got these erratic boulders, and they may and often do have very different rock makeup to the surrounding rocks. Okay, so again, this is why in some ways they're known as erratics. So what about how a glacier forms and changes as it moves downhill. And what we see in this particular figure here is a zone of accumulation, a zone of ablation, and an equilibrium area between the two. And what we're basically considering is a mass balance, a balance between a increase in mass, so increase in the solid mass of ice and snow at the higher areas of the glacier, and a loss of mass, or a net loss of mass, in terms of ablation. It's being ablated and it's losing mass in the lower parts of the glacial system, and the equilibrium line is where these masses are balanced. So this is where the mass of zone of accumulation and the mass of zone of ablation are equal at the equilibrium line here. So we have, just to sort of review here, a glacier forming where accumulation, okay, so this mass accumulation of snow and ice exceeds loss. Okay, so this is in this upper region, of course. And really throughout the travel and position of the whole glacier, it's losing mass, so it's losing ice and snow mass by these processes of melting, also erosion, and finally by sublimation. Sublimation is the process where solid water moves directly to water vapor without going through the liquid phase. So it actually does this at lower temperatures, and of course we're typically in regions where we have low temperatures and also certain pressure conditions which allow no melting to take place. So it does this below the melting temperature of water and moves straight from a solid to a gas. But we have these processes of loss over the whole glacier itself, except that we still have this mass balance. So we still have a higher accumulation of mass versus a mass loss here at the zone of ablation. And just to include this equilibrium line again, okay, so we've got the equilibrium line where these masses are equal, and as we just mentioned before, we also have the melt-out region. So we have meltwater produced at the base of the glacier, or the lowest elevations, where we have ice melting away and taken away in streams and rivers and so forth. Another feature that we can recognize in clean glaciers, which don't have much debris on the surface, is the actual zone of ablation here, sorry, the zone of accumulation here, and the zone of ablation in specific changes in colour. So the zone of accumulation is white, and the zone of ablation where we're losing mass is blue. And so we can actually eye in here pretty much where the equilibrium line, where these two guys are at balance somewhere in the middle of this glacier here. So what about movement of glaciers? And as it says here, we've got movement either by moving at the base, so by slipping, along the base, and also movement of shearing, so internal shearing of ice crystals and the flow of ice crystals. So two processes of movement in a glacier itself as it moves down valley, and of course again, as with lots of processes on the surface of the Earth, this is under the force of gravity. Now, because of the shearing process, the internal shearing process, the upper surface fractures, and this is how we form crevasses. This is why it's all kind of like dislocated and beaten up on the surface, and we've got crevasses and fractures and so forth. If we look at these processes of movement in a little bit more detail, we can have situations where the base of the glacier, and this is typical of certain types of glacier, but the base of the glacier is locked. So it's frozen here at the base, and there's no movement at the base. As it says, it's dry and it has irregularities, so there's high friction as well. And we therefore, the only movement we have is shearing. We still have movement, but we have some sort of gradient of movement moving through the ice, so the uppermost parts of the ice are moving the most through shear. And the other example is a base which is moving. It's moving. It may be smoother. It is also typically wetter. We quite often have channels and even big rivers and so forth in the bottom of the ice, which help to allow the glacier to move both at the base as well as shearing processes at the surface. Last slide here is indicating what happens when a glacier encounters water. Well, as a glacier moves out into water, and of course not all glaciers do, but if they move out into a lake or into the sea, as shown here, the water floats. The water floats on the ice, and it starts to actually move faster, and it starts to crevasse even more. It fractures up even more as a result. So the glacier may begin to float on water, and the floating ice spreads out, moves faster, and fractures. And this in turn begins this process of calving, of the collapse of large blocks of ice from the front of the glacier, which then move out as icebergs. So this is how we produce bergs, our iceberg factory, if you like. We also have another indication here of falling stones, and this is more evidence of glacial or past glaciers. What we would have here at the bottom of this sea or a lake, for example, are very fine layers of sediments which have stones that have fallen from icebergs embedded in them, and these are known as drop stones, and again another important piece of evidence of past glaciers being in water above these particular sediments. And so the falling stones, of course, are entrained into the icebergs, and as these parts melt out, then the stones fall as drop stones and make their way into the sediments below.